Uh, Hello. The red person is actually me. I hope you get some ideas on what I'm gonna talk about. Good afternoon, everyone. I'm Yi Xingzhu. Today, I'm gonna present our work on inferring forces and learning human utilities from videos. This is a joint work with from UCLA Center for Vision, Cognition, Learning, and Autonomy, and UCLA Computer Graphics and Vision Lab. Fan Fu, the co-first author, and Yi Biao, the third author, are also here. They will join me on a post session later. So in this paper, we take sitting behaviors and choosing chairs as the example. Here we show two concrete examples of sitting activities in an office and a meeting room. In addition to geometry and appearance, people also consider other important factors, including material, comfortability, and even social goals when choosing a chair. The histogram here indicates human preference for different candidate chairs. In this paper, we propose to go beyond geometry compatibility and infer the forces through physics-based simulation. Thus, our system is able to fill the comfort interval. In the first section, I will introduce our framework on how to infer the invisible forces from videos. Inferring forces takes 3 steps: watertight scene reconstruction, volumetric human poses modeling, and physics-based simulation. We reconstruct 3D scene with global optimization based on line processes, resulting in detailed reconstruction with loop closure. From reconstructed 3D indoor scenes, we uniformly sample vertices in the input mesh with Poisson disk sampling. By adding a ground geometry, we obtain a detailed reconstruction of a watertight 3D scene. The second step is volumetric human pose. The volumetric human pose is obtained with 3 steps: skeleton alignment and clustering, skeleton skinning, and volumetric discretization. Combining reconstructed watertight scenes with volumetric human pose, we obtain a fine detailed reconstruction. The final step is physics-based simulations. We use a finite element method to simulate human tissue dynamics. The output of the simulation are the physical quantities, in these cases, forces and pressures. In the second section, I will introduce learning and inference human utilities based on rational choice assumptions. I'll briefly talk about the features we use, including the spatial, temporal, and the physical quantities. Then I will introduce the formulation on the learning and the inference. Given a reconstructed 3D scene, we remove the ground floor by setting a depth threshold and projecting it onto a 2D map from a top view. 3D objects in the scene are first segmented into primitives and then grouped into object segments. Spatial features are defined as human object and object relatively distance and orientations. For each object, the geometry center is obtained by averaging over all the vertices. The human head position and orientation is acquired with a kinect. Temporal features are defined as a planning cost from a given initial position to a goal position. We use a probabilistic roadmap planner to calculate the cost. Physical quantities produced by people interacting with things are computed with the finite element method. An example is shown here. In the learning, by assuming human choice is rational, we treat the human demonstration as near optimal, thus treated as positive examples. If we imagine the same person making random sitting behavior, for instance, sitting on the floor, it is highly unlikely it will outperform human demonstration. Thus, we treat it as negative examples. Learning the ranking function is to find the weights so that the max number of following inequality is satisfied. Here we show how we generate different configuration using different poses, translations, and orientations. Then we will approximate the solution by introducing the non-negative slack variables and solve it using ranking SVM. During the inference, given a static scene, the goal is to in the inference phase is to find the best configuration among all the imagined configurations in the solution space. Here we show some experiment result. In the learning, the final forces histogram of 6 out of 14 body parts are shown here. Unsurprisingly, during sitting, forces act on the hip in almost all the cases. Upper legs and lower arms also tend to be subject to relatively large magnitude forces. Upper arms and heads are much less likely to interact with the scene, and the feet contact with the scene in many cases, but with overall small force magnitude. We then take the average forces act on each human body parts from all the collected human sitting behavior. The heat map of the average force is shown here. Here we show some inference result. Although using physical quantities produce physically plausible sitting poses, some of the results here do not look like sitting poses. For example, lying poses and upside down poses. Such diverse results are caused by the lack of spatial and temporal constraints. After adding the spatial features, the relatively orientations and the distance between the human models and objects in the scene improve the results. Intuitively, the top poses become more natural because they share similar human attention and social goals to those in the observed demonstration. When the temporal features are further integrated, the planning cost is taken into consideration. It is worth noting that the planning cost using the temporal feature enables our system to output a dynamic moving sequence, which extends the static sitting pose in previous work. Here are some more results in various scenes. That concludes my talk. Thanks.